Let's do another example. So we're going to sketch one period of each of these functions. Part A and B will be incredibly similar, and part C and D will be incredibly similar. So let's start with A, and we'll do A pretty much at the same time as B. So first we'll have to figure out the midline and the top and bottom line. So for the midline, we'll take the y value of 0 and we'll apply the transformations that are here. Now if f of t is the sine function, then this here can be written as 3 times f of 1/2 t plus pi over 2. And the vertical transformations that are being applied that will affect the midline and the top and bottom line are, well, is, because there's only one, this multiplication of 3, which is a vertical stretch by a factor of 3. So we'll take the old midline of y equals 0, multiply it by 3, and get 0. Then we'll get the top and bottom line. We'll take our old top line of y equals 1, multiply it by 3, and get 3. And we'll take our old bottom line of -1, multiply it by 3, and get -3. And so our midline is y equals 0. Our top and bottom lines are y equals 3 and y equals -3. Let's go ahead and sketch those. I like to do the sketches along the way as I figure out things. So there's a ty plane. Create a scaling here. Let's let that be 1. And then that would be -3. And this would be +3. And I'll go ahead and draw in my midline. I like to do this in a little bit bolder line here. So there's my midline. Here's my top line, and here's my bottom line. Now let's get our important t-coordinates. That's our second step. And to do that, we'll need the horizontal transformations. Now, keep in mind that we have a horizontal shift and we have a horizontal stretch. So 1/2 t plus pi over 2, so 3 1/2 t plus pi over 2. And when we have a mix of those transformations, the order will matter. And it's easy to figure out the order if you factor out this 1/2. So this 1/2 gets factored out, and we have t plus pi. Essentially, if you have a transformation that looks like this, where the number multiplying the t is not multiplying this pi over 2, you're going to want to factor out that number that's multiplying the t, in this case 1/2, from both of the first term, 1/2 t, and the second term, which in this case is pi over 2. Once you do this, you can identify the transformations and their order by putting the shifts last. So the horizontal transformations is that this is a horizontal stretch by a factor of 2. And this is a horizontal shift to the left by pi. And so to get my 5 t-coordinates, I'm going to apply these transformations to the first and the last. So the first t-coordinate is 0. You do 0, you multiply it by 2, and then you shift left by pi, and what you get is -pi. And then the last t-coordinate, remember if you have a number line, we're looking for the 5 important t-coordinates. I find the first and the fifth. First, to get the 5th t-coordinate, you take the 5th t-coordinate of the parent function, which is 2 pi. You multiply by 2, you subtract pi. So in this case, you would get 4 pi minus pi, which is 3 pi. Then you can get the third by figuring out what's halfway between the first and the fifth. And I'll remark that there will be a lot of problems where you'll just be able to look at this and be able to tell what the answer is. So what do I mean by that? What number is halfway between minus pi and 3 pi? Well, the difference between them is 4 pi, and so halfway between these two should be pi. If you can't see that, then you can simply just do the calculation every time of taking the average, minus pi plus 3 pi divided by 2. 3 pi minus pi would be 2 pi, so this is 2 pi divided by 2, which is indeed pi. Pi is halfway between minus pi and 3 pi. So that gives me my third coordinate. My second coordinate is halfway between the first and the third. So my second coordinate will be minus pi plus the third coordinate, which is pi divided by 2. Minus pi plus pi is just 0. And finally, to get my fourth coordinate, I need the average of the third and the fifth. So pi plus 3 pi divided by 2. Pi plus 3 pi divided by 2. That's 4 pi over 2, which is 2 pi. Once again, I'll make the obligatory remark that you could apply the transformations that are listed here to the important t-values of the parent function, that is 0, pi over 2, pi, 3 pi over 2, and 2 pi, and you would get these same results. Now let's go ahead and put these onto a coordinate plane. So in order to do that, I'll need to create a scaling here, and I think I'll go ahead and let this be my scaling. So I want that to be a distance of pi. In these problems, it can be kind of an art to figure out what your scaling is. Essentially, you want to pick something that allows you to fit all of those important t-values on the t-axis, but you also want to pick something so that they're not too crunched together. So let me show you a bad choice, and maybe that will help display what I mean. So if I chose this to be minus pi, then all of my t-coordinates would be extremely close to one another, and my graph would be very crunched. So I'm giving myself enough room so that I can fit all the t-coordinates on the t-axis, and I have room to draw my graph. Now, once you say that this distance is minus pi, you're also constrained to make sure that this distance is pi, because your scaling has to be consistent. That is, you couldn't have something like this is minus pi and this is 2 pi. That changes the t-scaling, and this second distance isn't the same as the first distance, even though visually it is. So I'm going to choose that this here is minus pi, and then this will become pi. And then if I go a little bit more, then let's see, is that enough? Yep, this would be 2 pi, this would be 3 pi, and I think I need 0 as well. So let's check to make sure I have all the coordinates I need. I have 2 pi on there, I have 3 pi, minus pi, pi, and 0. So now I have my important t-coordinates, I have my midline and my upper and lower lines. In part A, we were sketching 3 sine of 1/2 t plus pi over 2. And so since this is a sine function without a negative out front, there's no negative, then I will start at the midline, at the first important t-value, and then I will go to the upper line, and if there was a negative out front, I would have went to the bottom first, but there's not. Then I go back to the midline. I don't know why I marked this one with a star and the other ones with solid circles, so let's be consistent. So midline to the top, back to the midline, to the bottom, and then back to the midline, and we connect with a smooth curve. That, of course, resembles the original curve of the parent function. I don't know why this negative is still here. Let's go ahead and erase that. And then we can go ahead and work with part B, which was the cosine version. And I'll do this in yellow, and we'll do almost the exact same thing. Parts. So remember, there's 3 steps to doing this, and the first 2 steps are done. We've drawn our midline and our important t-values. Now we'll just copy the behavior of the cosine parent graph, which starts at the top, goes to the midline, then goes to the bottom, and goes back to the midline and back to the top. And we'll draw our smooth curve. For good measure, let's go ahead and graph -3 cosine of 1/2 t plus pi over 2. So we would have done the exact same work to figure out the midline and the important t-values. Then we would start at the bottom instead of the top, go to the midline, then up top, then back to the midline, then back to the bottom, and connect with a smooth curve. That, of course, represents the cosine curve of the parent function.